far beyond the familiar stars visible in our night sky. In a quiet region of the constellation Leo, a faint change in infrared light reached Earth after traveling through the darkness of space for more than a century. At first glance, it appeared to be just another stream of scientific data, one more collection of numbers among the trillions recorded by humanity's most powerful space telescope. But hidden within that light was something no one expected to find. Embedded in the planet's atmospheric spectrum was a chemical signature unlike those produced by rocks, oceans, or storms. Instead, it resembled a molecule associated with biological activity. The James Webb Space Telescope had observed a distant world with an atmosphere so intriguing that it quickly became one of the most discussed exoplanets in modern astronomy. Rather than simply suggesting that life could exist elsewhere, the observations raised the possibility that this planet may possess conditions capable of supporting it. The discovery emerged quietly from infrared observations collected as the planet passed in front of its parent star. During this transit, a tiny fraction of the star's light filtered through the planet's atmosphere before reaching Webb's instruments. Different atmospheric gases absorbed specific wavelengths of that light, leaving behind a unique spectral fingerprint that scientists could analyze. Researchers first identified familiar molecules, including water vapor, methane, and carbon dioxide. Each of these compounds is scientifically important because they provide valuable clues about the planet's atmosphere and chemistry. However, the greatest excitement centered on a possible detection of dimethyl sulfide, DMS, a molecule that, on Earth, is produced primarily by marine microorganisms such as phytoplankton. While DMS is considered a potential biosignature, astronomers emphasize that its detection remains tentative and requires additional observations before any biological interpretation can be confirmed. The planet, known as K2-18b, orbits a red dwarf star approximately 120 light-years from Earth within the star's habitable zone, the region where temperatures could allow liquid water to exist under suitable atmospheric conditions. Unlike Earth, however, K2-18b does not belong to the category of small rocky planets. It is classified as a sub-Neptune, a world significantly larger and more massive than Earth, with a thick atmosphere believed to contain abundant hydrogen. Rather than automatically making the planet hostile, this hydrogen-rich atmosphere has led scientists to propose that K2-18b could belong to a theoretical class of worlds known as Hycean planets, planets with hydrogen-rich atmospheres that may contain deep global oceans beneath them. Although this idea remains under active investigation, it has expanded astronomers' thinking about where habitable environments might exist beyond our solar system. Current models suggest that K2-18b may possess a relatively stable environment. Its atmosphere could trap heat efficiently, reducing extreme temperature variations across the planet. If a global ocean exists beneath the atmosphere, such stability might create conditions favorable for maintaining liquid water over long periods. Because the planet is likely tidally locked to its star, one side may permanently face the star while the opposite side remains in continuous darkness. Even so, atmospheric circulation could redistribute heat around the globe, preventing dramatic differences between the two hemispheres. Its greater mass and stronger gravity also allow the planet to retain its atmosphere far more effectively than smaller worlds such as Mars, which gradually lost much of its atmosphere billions of years ago. Although conditions on K2-18b would almost certainly be very different from those on Earth, researchers are increasingly recognizing that life may not require environments identical to our own. Instead, thick atmospheres, stable temperatures, and abundant liquid water, if present, could potentially provide suitable conditions for biology to emerge and evolve over immense spans of time. The planet's parent star is a red dwarf, much smaller and cooler than our Sun but capable of shining for trillions of years. While our Sun is expected to eventually exhaust its fuel and expand into a red giant, red dwarfs burn their fuel extremely slowly, offering extraordinary long-term stability. K2-18b completes one orbit around its star approximately every 33 days, while receiving a level of stellar energy comparable to that received by Earth from the Sun. This places the planet comfortably within its star's habitable zone. Because red dwarfs remain stable for such immense periods, any potentially habitable planets orbiting them could enjoy conditions suitable for life far longer than Earth is expected to. Combined with its dense atmosphere, which may shield the planet from harmful radiation while redistributing heat globally, K2-18b has become one of the strongest candidates for studying potentially habitable environments beyond our solar system. Its discovery has encouraged astronomers to reconsider long-held assumptions about where life might exist. Instead of focusing exclusively on Earth-sized rocky planets, scientists are now exploring the possibility that larger, warmer worlds with thick hydrogen atmospheres may also offer environments capable of supporting biology. Perhaps the most intriguing aspect of the discovery is not simply the planet's size, orbit, or temperature, but the chemistry of its atmosphere. The gases detected by Webb appear to exist in a state known as chemical disequilibrium. Under ordinary circumstances, many atmospheric gases react with one another over time, until they reach a stable chemical balance. On Earth, however, biological processes constantly replenish certain gases, preventing the atmosphere from reaching equilibrium. The atmospheric composition observed on K2-18b may display a similar pattern, making it an exceptionally important target for future study. However, scientists caution that chemical disequilibrium alone does not prove the existence of life. Geological processes, unknown atmospheric chemistry, or other natural mechanisms could also contribute to these observations.